What's going on, everybody? It's Mr. Gus, and I'm back in the physics classroom. We're looking at the How High lab today, okay? So we just finished up our study of one-dimensional motion. We've begun free fall a little bit here, but now we're looking at some more properties of free fall. For objects that undergo motion, I'm on the wrong side, motion that looks something like this, okay? So here's the lab. We went outside, we took objects like baseballs, tennis balls, Nerf guns, and we shot them or tossed them straight up. I'm talking straight up, vertically. No horizontal motion whatsoever. Straight up, straight back down. And I sketch it like this, where it looks like kind of a parabola because it's easier to see the different positions, but we really didn't want it to go left and right. We wanted to go straight up and straight back down. And we took some data on this thing. The only data we really needed to take was the amount of time it took to get from point A to point C. We didn't need to take the time to point B because we knew that point B was the half time. However long it takes to go up to point B should be the same time it takes down to go back down to point C. So essentially literally all we did, just on a much grander scale, was we took an object, we threw it up, and tossed it back down. That's it. That was the extent of the lab and the data gathering. I didn't have height. I couldn't measure height. The only thing I had was a stopwatch and the projectile. So the only data we got was time data, and really, like I said, the only data we got was this 3 seconds right here. Now we divide that by 2 because the lab says, and we know that if it takes 3 seconds to go up and come back down, it's going to take 1.5 seconds to get to the top. So that's the data you need. Add that to your lab if you weren't here, or if you have bad data, you can use this data, whatever. From A to B is 1.5 seconds, and from A to C is 3 seconds. Now, caveat, points D and E are not a quarter of the time. They are only half of the total height. So it's not half time or half time or quarter time. It's not about time. D and E are only about height. So D and E are half the height on the way up, and E is half the height on the way back down. So we can go ahead and toss that into our data table over here, where I look at points A through E. Out of order a little bit, it goes A, D, B, E, C, because A, B, and C, I think, are the easier points to deal with because of where they are. So I start with A, B, and C, then I come back to D and E. So let's talk. The displacement, or the origin, is A. We're going to call wherever we launched it from, that was a height of 0 meters. Again, I didn't have a meter stick to measure, but I get to pick my arbitrary point in space to call that 0. So I'm calling point A 0, and because it's perfectly symmetric, we catch it or stop it right when it comes back down to the same height, we're calling C 0 as well. Those are the only 2 heights I know. I wasn't given a meter stick. I just know where I start and where I end. The other thing that I know about this projectile is that if it is going to travel up and then back down, at some point it has to stop, turn around, and come back down. And that point is point B. So where it's stopping and changing directions, that's point B, that's my velocity. So at point B, the velocity of this projectile, this dart, this Nerf dart, baseball, tennis ball, what have you, is 0 meters per second. The other thing that I know, because I am a good physics student and I draw pictures of things, is that the only force acting on my object is the force of gravity. Now that's weird to think about because of the different motion at points A, B, and C. So let's track that, right? So at point A, this is my force. These are the forces acting on it at all points. The only force acting on it after it leaves the launcher is gravity. We're going to neglect air resistance in this lab because it's negligible for things like baseballs and tennis balls when we're moving at such a low velocity. The Nerf dart may have more air resistance, but let's ignore that for now, okay? So at point A, my picture would look something like this. There's a force of gravity downward, but the motion is upward. At point B, the force of gravity is still downward, and there is no motion. It's coming to a stop at its apex. And then for point C, we still have the force of gravity, but now its velocity is downward. So 3 different instances, but in all 3 cases, we have the same force acting on it, which means we'll have the same acceleration. My battery's going to die. Give me 1 second to plug this thing in. While you're sitting there waiting for me to get my charger, I want you to think about, if my force remains the same, what does that mean for my acceleration? Is my acceleration changing, or do I have the same acceleration throughout? Again, forces cause accelerations. They cause changes in motion. So if gravity is the only force acting on it, if gravity is what's causing a change in velocity, then my acceleration must be what we discovered in the bleachers lab. My acceleration must always be pointed downward in the same direction as the force, and it must also be equal to baby g. So 9.8 meters per second squared is my acceleration for this object throughout its path. Since the force never changes, my acceleration also will not change. It will be pointed downward, which I'm going to call negative, and it will be 9.8 meters per second squared. If I included air resistance in this lab, that acceleration would change a little bit because there would be another force acting on it. But again, we've neglected air resistance, so now our acceleration is baby g, negative 9.8 towards the center of the Earth. These are the things I know. So we started with this blank table and not a lot of information, and at this point, we kind of know a lot of information. We have a lot of the blanks filled in already. So now it's just time, to figure it out. Let's figure out how I can find the velocity initially here. How can I find the displacement to point B? How can I find the velocity at point C? So now it's just a chance to kind of pick and choose equations for us. So let's start with A. What equation might I use for A? Let's think about what I know. I'm going to write over here the things that I know, my known variables, and over here, I'm going to pick an equation to use. So I'm going to need some space. I'm going to go ahead and erase my awesome pictures, but you should still have yours in your science notebook or in your packet. So over here, I know my initial position. I don't know my final position. I don't know where it's headed exactly, right? I'm not exactly sure where it's heading. I know acceleration here. I know time to the apex, so I know time to the top to point B. That's helpful, but I don't know initial velocity. So I know acceleration, I know position. If only there was an equation that included some of these things that would help me. Oh, I guess I do know final velocity. If I'm going to B, I know the velocity at point B. That's helpful. An equation that includes these things. Let's see here. Wait, velocity, acceleration, time. I'm solving for a velocity. I can go ahead and use that my velocity at B is going to be equal to my velocity at A plus the acceleration times time, and that's time to B. I'll let you look at our picture and our data and our data table and solve that equation for that. Go ahead and do that, okay? I think the same is probably true over here for my knowns. I know my position down here. I know my acceleration at C. I know the time it takes to get from B to C. I know that. I also know the velocity at B. I can probably go ahead and do a similar equation where the velocity at C is equal to the velocity at B plus the acceleration times the time from B to C. And again, you can use our picture and our data to figure those things out. I'm using different velocities at different locations and the times between those locations. You can probably figure that one out. B is a little trickier because now I'm looking for displacement. So, to find B, I need something that's got velocity in it and position in it. I also have time, so I know time. Now that I've solved A and C, I know the velocity at A, I know the velocity at C. I don't know position, but I'm looking for position. I certainly know acceleration. Folks, you can use pretty much any equation you want here to solve for this, as long as you're differentiating between A and C. Let's see. My initial velocity isn't 0, so the quadratic, it's messy. I'm not a big fan of it. So maybe we should use this one. Let's use our velocity at B squared is equal to the velocity at A squared plus 2 times the acceleration times, we're going to call it change in Y in this case because it's vertical. So I could probably use that equation to find the displacement to point B. All right? Once I have that, E is the height is just half of B, and same with D. And I'm not going to solve those ones for you. I'm not going to pick those equations for you. I'm going to give you a chance to figure those out on your own, figure out their displacements and their velocities. This is a lot of great math practice with our kinematic equations, using the idea that because this object is in free fall, only experiencing gravity as a force on it, its acceleration is negative 9.8 meters per second downward. All right? So do this math. Figure out the proper equations to use. Tomorrow or the next day in class, our next discussion will be on what are some things you notice in common or some weird similarities and symmetries we see about this motion as it travels from A to B to C. And can we use those symmetries to our advantage moving forward with projectile motion and vertical motion? Okay? Until then, see ya!